Um, Good afternoon, everyone. I'm Kesar, and we're going to be discussing cross-domain transferability of adversarial perturbation, a paper by Muzamil Nasir, Salman Khan, Mohammad Haris Khan, Fahd Shahbaz Khan, and Fatih Berkeley. Me and my groupmate Daniel will be going over each of these slides. This was presented in the 33rd NeurIPS conference held in Vancouver, Canada. It has 21 citations, and the link to the GitHub repo is provided over here. We'll be discussing the introduction first, followed by some related work, some proposed methods, such as the GAN model that they use, the discriminator loss that they use for this, um, which is a derivation of the relativistic cross-entropy loss, some of the experiments that they conduct, results, conclusion, and then for and against. So they identify the motivation behind this paper was they identify certain problems that normal adversarial attacks have, and some of them are most of the attacks are instance specific, which iteratively optimize a perturbation pattern specific to an input sample, and they're instance agnostic, where the model tries to learn a universal function that can fool most of the images. Some of the contribution that they have for this paper is they introduce a domain agnostic model that can fool any of the model with a different data distribution. They propose a transferable adversarial GAN model that can be used to generate these adversarial examples. And to do so, they use something called the relativistic loss, which will be covered in the future slides. Now, what we can do with this paper is the model is highly scalable. So once the universal function is learned, we can uh, leverage it on other data distributions. They explain it in this paper by using paintings, cartoons, and medical images on which the generator is trained on, and they successfully perturb ImageNet validation data. So let's see some of the related work that they cover. They split it into three different categories. The image dependent perturbations. Here, this is the attacks that we see mostly in this class. And we, the gradient ascent step is applied on the pixel space. So to maximize the loss basically. This is done in a mutually exclusive way for each data point specifically. And then we have universal adversarial perturbation, which tries to add a single noise vector to the image to fool the pre-trained model. But this too is done in an iterative fashion for each of the data point. And then something that we haven't covered before, but the authors touch, is the generator-oriented perturbations, where a generator is used to find the adversarial examples. But most of the previous works have unbounded perturbations where there is no budget or an epsilon value. And they rely on the data distribution in a direct or an indirect way. In this paper, they compare a few of those models along with theirs. Here we can see what kind of data it's trained on, the transferability strength, and whether it is label agnostic or data agnostic, which means it's cross-domain. So we can see only their method is both and being transferable. So let's look at the model itself now. We can train this GAN model using different data distributions. Hence, it is a cross-domain model. On top of this, the model itself is an adversarially modified traditional GAN model where the generator has some downsampling, residual, and upsampling blocks, while the discriminator is just a standard classifier. Now, this can be trained as a targeted or an untargeted method as well. They propose loss functions for both. and then they project the perturbations back onto the L infinity ball. Here, the generator's goal is to create adversarial examples, while the discriminator's goal is to output class probabilities since it's just a pre-trained model. Once it has been trained on these data sets, it can be used on different data sets such as ImageNet, use the same generator and our pre-trained model that we need to fool. So they propose something called the relativistic loss, and I'll explain how it's different from what we already use in the GAN model. In a traditional GAN model, they have something called a binary loss, which either outputs if the image that has been generated by the generator is either real or fake. But in transferable GAN model, since the discriminator is a pre-trained classifier, it just predicts the value between 0 to the number of classes. So here, if this is the discriminator loss, then our loss should be, our perturbations should be, the L infinity term of the perturbation should be less than the epsilon value, that is our budget, and the maximum value of our discriminator loss on the adversarial example should not be equal to the clean example, and the gap should also be higher than the fooling rate. So they try to bring about the use of the clean image and the adversarial image. So in a traditional GAN, the transferability is low because it doesn't account for clean predictions. This is the loss for a normal GAN model, which just has adversarial image in it. And this is the one hot encoded vector, and they're trying to maximize the cross entropy loss here. But for relativistic loss, which is inspired by relativistic objective function, they propose an untargeted function that tries to maximize the gap between the adversarial output and the clean output. What this helps us go further away from the clean image, basically. And in terms of a targeted model, we already have a label, and it should not be equal to the clean image label. So for that, the targeted label, they propose a loss function where they're trying to maximize each of those discriminator losses individually, and they sum them up. So this is a comparison between the cross-entropy loss and the relativistic cross-entropy loss. These graphs, these models are trained on VGG16 with 100 random images. So here we can see the loss of the relativistic cross-entropy loss converges way faster than the cross-entropy loss. This describes the loss trend over iterations, and this is the gradients itself that we get. So looking into the algorithm and the model itself in much more depth, we have the input distribution, which is our data set, which can be painting, medical images, or anything. And we send it through the generator. Now the generator predicts unbounded perturbations that go beyond the budget that we have. And we project it back onto the L infinity norm. And then we send this generated example to the pre-trained classifier. And whatever the pre-trained classifier's output we get is then sent to the relativistic. So if we look at the algorithm itself, we randomly initialize the generator parameters in the beginning, and we send in mini batches of training sets. The generator in its current state outputs unbounded perturbations, but then we, in order to get it back onto the valid perturbation budget, we project it back onto the L infinity norm and then get a standard image. This is forward passed through the pre-trained classifier whose weights remain constant throughout. This output is used in our relativistic loss, and then we only tune the generator parameters. The pre-trained classifier remains the same. Basically, the discriminator remains the same. We repeat this process until the model converges. So they describe how relativistic cross-entropy is better than the cross-entropy loss. And if this is our cross-entropy loss, they take P of y as the softmax function to make it simpler for derivation. So now we can look at cross-entropy and relativistic cross-entropy losses side by side and their partial derivatives. So if we define our losses such as this, the relativistic cross-entropy will be the perturbated image minus the clean image, since we're trying to maximize this gap. So the partial derivative of P of y with respect to A of I will be given as this. This basically means whenever I is equal to y, this is 1. When I is not equal to y, it is 0. And this becomes minus py into P of y. Similarly, let me explain this in depth. Yeah, P of y basically means this is 1 whenever I is equal to y. If not, it's 0. So then here for R, they use the perturbations instead of just the softmax, where they take the difference of the adversarial image versus the clean image. And then we get this when we partially derive that with respect to A of I. And then using chain rule, dou CE by dou P into dou P by dou AI would be this minus 1 or 0 here. Similarly, we get the same with relativistic cross-entropy, where the perturbation minus 1 or 0 whenever I is equal to y. Now, the advantages of this is the RCE tries to maximize the difference itself. So the gradient strengths will be larger for relativistic loss compared to the cross-entropy loss. Further, they also mention that since they don't have access to the label space itself, whatever the prediction that the model generates, it'll just be farther away from that. So the model misclassifies the image no matter we use the label space or not. So the gradient strength of RC will always be greater than the cross-entropy loss. They compare this with different models, pre-trained models, and here we can clearly see that relativistic cross-entropy loss performs way better. And the transferability, this is the fooling rate itself. The metric used is the fooling rate, and it is tested on the ImageNet val data, while the generator was trained on the painting dataset using a ResNet 152 model.
So now that we have an idea of how this generative model is trained, and specifically how the authors leverage this relativistic loss to backpropagate stronger gradients, we're going to take a look at some of the experiments and results this paper presents. So first off, we're just going to describe the experimental settings. So for all models, they use the Atom optimizer, and I also describe here the learning rate and exponential decay parameters that are used during training. So we mentioned in order to train the generator itself, we leverage a couple of different frozen classification discriminators. So specifically for these experiments, the authors leverage 5 different pre-trained classifiers, including VGG, Inception, ResNet, and this ChexNet model, which is a dense net trained to diagnose pneumonia from X-ray images specifically. So again, during the training of the generator, these discriminators are frozen. So we're only updating the weights of the generator. I can't click through the slides. Okay, now I'm getting. Okay, so we also mentioned that this generator can be applied across different data sets. So specifically, they leverage 3 different data sets during training to train the generator, and then during evaluation, they use ImageNet. So the 3 data sets they use to train the generator are this paintings data set, a comics data set, and a chest X-ray data set. And then during evaluation time, they attempt to perturb ImageNet, and they use the fooling rate for the evaluation metric. So they perform experiments in 3 different settings. The easiest setting is one that we're familiar with, which is a white box setting, where we have access to both the model parameters as well as the training data this model was trained on for evaluation. Then a more difficult scenario is when we do not have access to the model weights themselves, which we're going to use for evaluation, but we do have access to the training data set itself during evaluation. So that's known as a black box setting. And the most difficult scenario is the cross-domain black box scenario, where we have access to neither the model parameters nor the training data. So in this case, we have to train our generator both on different images that are used during evaluation, and also using different discriminators themselves. So the first set of experiments we're going to take a look at are the cross-domain black box experiments. So here they train their generator using the ChecksNet model as a discriminator, and they also train 3 different generators, each of which on the 3 separate data sets. So they train a separate generator on the paintings, comics, and chest X-ray data set respectively. And for the first set of experiments here, they use a maximum perturbation magnitude of 10. They also use Gaussian noise as a baseline attack to compare their generative attack to. And the columns here represent the discriminators that are used during evaluation time. Again, we're using the ChecksNet model itself during training time. So this is a cross-domain setting because we're not only using a different training set than we're going to use during evaluation time, but also different discriminators as well. So looking at the first set of results here, we see that first off, their generative attack strongly outperforms their baseline Gaussian noise attack. And then we also see that the comics data set tends to produce the strongest results. The paintings data set also results in pretty good results, and the chest X-ray data set results in significantly weaker performance than the other 2 data sets. So the authors touch on this, saying the chest X-ray data set lacks texture, which they find to be important for perturbing ImageNet images. Therefore, they find that the paintings and comics data sets are most effective for training their data set, and then they result in strong perturbations on ImageNet images during evaluation time. So they also conduct these experiments using a couple of different maximum perturbation magnitudes. So here, the next set of experiments uses a maximum magnitude of 16. And the results are consistent here, where the comics data set produces the strongest performance, and their generative attack continues to outperform the Gaussian noise. And they do perform 1 extra set of cross-domain black box experiments here with an epsilon value of 32. It's interesting to note here, as magnitude increases, now the chest X-ray data set is performing slightly better than the other 2 data sets. So that was interesting to see. The authors didn't include much discussion on that, which I would have liked to see, because it's interesting to see how the different data sets result in different performances, especially across different epsilon values. So the next set of experiments we're going to look at are black box and white box scenarios, and they're comparing their generative attack to other state-of-the-art universal perturbation methods. So one example of a universal perturbation method is the paper titled Universal Adversarial Perturbations, which they represent as UAP. And then FFF and AAA are other universal perturbation methods that we have not covered yet in class. So when we're looking at this experimental table here, this left column here represents the discriminator that is used during training. And these 3 columns here represent the discriminator that is used during evaluation time. Therefore, they used an asterisk here to represent the experiments that are performed in a white box scenario, because the model that's used during training and evaluation are the same. We see that the generative attack strongly outperforms these other state-of-the-art universal perturbations, both in white box and black box scenarios. The authors note that this transferability is due to the generator learning contrastive signals via that relativistic loss that then are agnostic to the discriminator. So that means you can basically use one discriminator during training time, and the perturbation will transfer to a different discriminator during evaluation time. It was interesting to note in these experiments that the data set itself doesn't seem to matter too much for the fooling rate here, both in white box and black box scenarios. So all three data sets result in around 99% fooling rate. It's also important to note that despite this middle column here technically being a black box setting, because we're using VGG 16 during training and 19 during evaluation, both VGG 16 and 19 are still quite similar models themselves. So that's why these results are quite similar, despite one being a white box and one being black box. So we really have to take a careful look at the third column here to really tell how this generative attack is doing in the black box scenario. And it's interesting to note that this universal adversarial perturbation method actually really strongly outperforms the generative model, which is very interesting to note. So we then changed the model during training time to VGG 19 and perform the same experiments, and the trend is the same, where this generative attack is actually outperformed by this other universal adversarial perturbation method. And the last row of experiments here are performed using ResNet 152 as the discriminator during training time. And so finally, we see here that this generative attack is outperforming the universal adversarial perturbation. So based off these results, this sort of begs the question, does this generative attack truly set a new state of the art for black box settings specifically? Because the only time this generative attack actually outperforms other state-of-the-art universal perturbation methods are in white box scenarios so these experiments here, these experiments, and these experiments are white box, and the generative attack outperforms the other state-of-the-arts. But in these more difficult black box scenarios, we're not setting a new state-of-the-art. And the authors don't touch on this at all. They sort of just present this table and say they're setting new state-of-the-arts for both white box and black box. But if you really examine the experimental results here, that's not truly the case in all of the experiments. So that was something interesting I noted when analyzing these results. Overall, though, the generative attack does outperform these other universal adversarial perturbations. So the next set of experiments which we're going to analyze are performed again in a black box scenario, but this time we're testing against adversarially trained ensemble models, where in the previous slide here, these models that we were testing against were just naturally trained using standard training procedures. So these models here that we're looking at are actually adversarially trained, so they're already a bit robust to adversarial perturbations. So we can take a look now how this generative attack performs against robust models. So again, they use 3 different data sets to train their generator, specifically paintings, comics, and ImageNet. So they're no longer using the X-ray data set because they found that that did not result in good performance. And then their generators here are only trained against a naturally trained Inception V3 model. So that's why they only really include like one model for each of these data sets, because they do not vary the discriminator during training time. So here, the first thing to note is that their generative attack continues to outperform other universal perturbation methods, shown here. And they also perform some experiments using Gaussian smoothing on the outputted perturbations, and that they find that Gaussian smoothing increases transferability, specifically against adversarially trained models. So again, this model that we're testing against during evaluation time was adversarially trained, and we find that Gaussian smoothing improves performance. So here's another set of experiments just using a different model during evaluation time. And this trend holds true, where Gaussian smoothing increases transferability on adversarial examples. And here's the final row of data where the trend again continues. So in general, this tells us when we're attacking adversarially trained model, it's better to attack with more general smooth over perturbations than the initial perturbations generated from this model. The last set of experiments we're going to look at are their comparison with other state-of-the-art instance-specific attacks. So thus far, we were comparing the author's generative attack to universal perturbation methods, and the next couple slides are going to compare against instance-specific attacks like FGSM. So for all of these experiments here, they use a maximum perturbation magnitude of 16. And again, they're going to show experiments for both black and white box scenarios. So this is a lot to intake here on one slide, but I had difficulty figuring out how to split up this table here. So again, they only include one model for each of the data sets they train on. So they only use, again, a naturally trained Inception v3 during the training time of their generator. And the instance-specific attacks they're comparing against are both FGSM and this diverse input methods attack, which we have not covered in class yet. And then they also include the momentum iterative version of FGSM, as well as the translation invariant variation of both of these attacks. So the first thing to note from these experiments is that this generative attack is outperforming all of these instance-specific attacks pretty strongly here if we compare their results. So this is very significant because this shows that this generative attack can both outperform state-of-the-art instance-specific methods as well as universal perturbation methods, which we looked at in the previous slides. So it shows that this generative attack can be used in a variety of different settings to really great effectiveness. The next set of the results here I brought in are results against adversarially trained models. So this set of results were against naturally trained models or models trained using a standard procedure. And this set of experiments are against models that were already trained to be robust to adversarial perturbations. So now we're going to compare the effects again of Gaussian smoothing on the performance against adversarially trained models. So I'll just hide away the rest of the results so we can focus on the bottom rows here. What they find is that Gaussian smoothing results in a slight decrease in transferability on naturally trained models, which is shown here. So again, if you're attacking a naturally trained model, it's best to not really include Gaussian smoothing, although they find it doesn't degrade performance too much. Although against adversarially trained models, Gaussian smoothing results in a significant increase in transferability, as highlighted in the green box here. So again, this is telling us that Gaussian smoothing performs well against adversarially trained models, and it doesn't improve performance too much against naturally trained models. So what we've covered so far is that this generative attack can outperform both instance-specific and universal perturbation methods, and that Gaussian smoothing improves performance against adversarially trained models specifically. So the next set of experiments we're going to take a look at are the author's analysis of the number of training epochs effect on the performance against both adversarial and naturally trained models. So here they include a graph of fooling rate against the number of training epochs used to train the generator. And what they find is that using a higher number of epochs improves performance against naturally trained models. And here's the same graph, although against adversarially trained models. And they find that the relationship is inversed. So when you're attacking adversarially trained models, which are already robust to these perturbations, we'd rather use a low number of epochs to train the generator. So again, there's an inverse relationship here between number of training epochs and fooling rate against adversarially trained models. The intuition behind this is that since our generator is trained only against naturally trained models, it will tend to converge to a solution space which the adversarially trained model has already seen. So the more number of training epochs we use, the stronger our generator will converge on a perturbation which an adversarially trained model is already robust to. So as a result, perturbations become weaker against adversarially trained models as the training progresses. So we've analyzed the effect of number of training epochs on the fooling rate itself. So now let's take a look, let's visualize these perturbations and see what the difference really looks like. So here are a couple of unrestricted perturbations that are generated from the generator. And as we go right in the columns, number of training epochs increases. And the row I've just brought in are these perturbations after projecting them back into the L infinity ball. So what we see here in general is that perturbations generated from a generator trained on low number of epochs seem to be a bit more noisy and more general, where higher number of epochs tends to converge on sort of a cleaner perturbation. So again, this is telling us that when we're attacking an adversarially trained model, we want to use sort of more noisy, more general perturbations. And this also provides some intuition behind why Gaussian smoothing improves performance against adversarially trained models. And when you're attacking a normal, naturally trained model, we can allow our generator to converge on a more clean perturbation because our naturally trained model is not robust to adversaries at all. And here's just another set of perturbations here, visualizing the effect on number of epochs on the actual perturbations themselves. And again, the trend continues where a low number of epochs result in these very noisy perturbations. And as epochs grow, we get sort of these cleaner, more converged perturbations. They also experiment with the Gaussian kernel size and attempt to quantify the performance of kernel size on fooling rate. So what they find is that on naturally trained images, first of all, not using Gaussian smoothing is preferable when you're attacking a naturally trained model. And also, kernel size has this inverse relationship with performance. So as we increase the kernel size, the fooling rate tends to degrade. They perform the same set of experiments here, although against an adversarially trained model. And here we see how Gaussian smoothing strongly improved performance. Although there's this sweet spot of the kernel size found at a 3x3 kernel. So against an adversarially trained model, we'd like to use Gaussian smoothing with this 3x3 kernel, but increasing the size continues to degrade performance. So what this is telling us is that against both naturally trained and adversarially trained models, kernel size has this inverse relationship with the transferability or fooling rate. So similarly to the previous slide, I'd also like to visualize the effect of kernel size on the perturbations themselves. So the first row of data which I've brought in are unrestricted perturbations generated by our generator. And the middle row here is the perturbation after applying Gaussian smoothing. And the last row is after projecting it back onto the L infinity ball. And then also as we go through the columns towards the right, our Gaussian kernel is increasing size. So as expected, as kernel size increases, the perturbations tend to become more and more noisy. So this very left row here would be the strongest performing perturbation. The authors also include some visualizations of the attention shift or feature shift on clean images and also their perturbed images. So the first row of data I've brought in here are clean images. So as expected, the attention or the features are focused mainly around where the object is present in the image. And so here we're visualizing the attention of the features on the perturbed image or the adversarial image. And so as expected, the attention is shifted off from the main object. I found this to be interesting because as expected, the attention shifts away from the main object, but the attention for most of these still tends to be focused around some small point. Whereas in some of the visualizations we've looked at in previous lectures, like the FGSM perturbations, PGD perturbations, if I remember correctly, they tend to shift the attention sort of like more noisily around the entire image, whereas this generative model learns to shift the attention away from the original or the main object in the image, but they're still focused around a small point here. So I think that's a benefit of these perturbations in general. And here's just one more row. So here are the clean images and their resulting adversarial images and the attention shift. So there are, of course, some perturbations which result in like a more noisy attention shift, but for the most part, the attention is shifted away from the main object, but still tends to be focused around a small point in the image. To conclude this presentation, I'm just going to visualize a couple more perturbations that are created with this generative attack. So here is a row of clean ImageNet images, and their ground truth labels are provided above each image. The middle row here is the unrestricted perturbation created by the generator, and the last row here is the final result after projecting back into the L-infinity ball, and I also provide the predictions of these adversarial images. So this was interesting to see. These predictions are generated from a discriminator that was trained on ImageNet. So it looks like this generator is learning for all of these images, this like sort of jigsaw puzzle looking perturbation. So again, these adversaries were generated from the untargeted version of the generative attack. So perhaps that's why, I guess if you were to use a targeted attack, you can control what this perturbation looks like more. So I'm not sure if you could consider that a weakness of the attack, in that this perturbation function is sort of always applying this jigsaw looking pattern to the images. And the last slide here is going to visualize the effect of the training data set itself on the generated perturbation. So again, the first row here is original images, middle row is unrestricted, and last row is after projecting into the L-infinity ball. And so these perturbations were generated from a generator that was trained on the paintings data set. So we need to pay very close attention to the actual perturbation pattern itself. So paintings tends to learn this sort of square-like pattern. So if we pay very close attention to the next animation here, we're going to switch from a generator trained on paintings to a generator trained on a comics data set, and we can see how that affects the perturbations themselves. So I've just switched here, and we can see how the perturbations generated from a generator that was trained on comics look visually very different from the previous model. And going once more, the next generator that we're going to show is trained on ImageNet. And again, we can see a slight difference in the actual perturbation pattern itself. So this is just visualizing how the training data set that's used does have an impact on the perturbation pattern itself. So in conclusion, the authors of this work show the existence of domain invariant transferable adversaries. To do this, they propose a novel generative framework that learns to generate strong adversaries using that relativistic loss and pre-trained discriminators. This generative attack shows state-of-the-art performance in all three scenarios, including white box, black box, and cross-domain scenarios. This attack outperforms competing universal adversarial perturbations as well as instance-specific methods. So just these two bullet points here demonstrate how powerful this attack is, and that you can apply it on a variety of different settings, and we can outperform both universal and instance-specific methods. By training a generator on X-rays, comics, and paintings, we can successfully perturb ImageNet images during test time. And this cross-domain fool rate reaches up to 88% without pre-knowledge of the data distribution or label space of the evaluation model. And lastly, the authors also show that Gaussian smoothing improves transferability to adversarially trained models specifically.
Now let's look at some arguments for the paper. It outperforms all instance-specific and agnostic models, as we saw, and it creates new state-of-the-art results for white box and black box setting. We consider this a huge leap in the universal adversarial perturbation domain, where the model itself is completely data independent. Um, they propose a generator whose inference time and efficiency is faster, as well as their transferability rates are also high. The proposed loss, which is the relativistic loss, is very flexible, and it is mostly distribution agnostic. Hence, it doesn't require um, the labels itself, that the target labels. Some of the points against this paper is they mentioned that the training itself is fast, generation of adversarial examples are relatively quicker, but they don't consider since they use a discriminator that's already a pre-trained classifier, they don't consider the expansive process beforehand. Similarly, when they mention that they don't have access to the label space, which is true, but they use the labels predicted by this pre-trained network in order to classify the fooling gap. So in a way, they are accessing the labels. Um, Something that's interesting as well is they mention the targeted loss for the relativistic loss, but they don't show any empirical results suggesting using the RCE targeted loss. So this questions the very equation itself, the loss equation. Some of the discussion points that we would like to put forward is whether the use of the labels or the targets would impact the adversarial examples drastically. And it would also be interesting to see these attacks against the auto attack, as we've seen before. Thank you.